I'm Tim Ventura from American Anti-Gravity, and today we're joined by Ed McCullough to discuss lunar and space colonization. Ed is an associate fellow at the American Institute for Aeronautics and Astronautics and the former chairman of the AIAA Space Colonization Technical Committee and Board of Trustees at the University Space Research Association. He's also formerly the Section E chairman of the ISNPS STAFE conference, which focused on innovative approaches to colonizing space. Well, Ed, thanks for joining us. I first met you back at the STAFE conference in 2006, and my impression was that you'd really assembled a dream team of visionaries on space colonization there. Can you tell us what STAFE meant to you and how it fits into the larger picture of emerging research into space and lunar colonization?
STAFE no longer exists in the form that it was in when you first met me. Essentially, what has happened is it's actually modulated into something that's smaller, and it's being carried on by a gentleman named Paul Murad. At the time, there were 5 different symposiums and conferences going on at STAFE, one of which was the Symposium on Space Colonization. The largest it ever got was up to, I think, 17 sessions. And at that point, the actual conferences stopped, not because of us, but because of the University of New Mexico decided to change their policy on the conference and the funding, et cetera. So that's the reason why that particular conference shut down. But I would say basically that it was an actually very good conference. We had phenomenal attendance. Everyone loved our symposiums. We had 4-hour-long plenaries that drew a lot of attention. And I think that at that point, we were able to get many very qualified presenters to come and to talk on many subjects. We even had a lot of representation by NASA in our plenary and in a lot of the actual sessions that we had. So from my point of view, that was sort of like a high point in the space colonization.
Well, I understand that STAFE 2 is carrying on some of the propulsion research that was underway. Are they also covering space colonization?
The space colonization, from my understanding, is not really very big at STAFE 2. We've been going to typical AIAA conferences like the Space Conference and Joint Propulsion Conference and things like that. But STAFE was the largest. As a matter of fact, it got to be big enough that it was turning into a problem for a lot of people because what they wanted to do is they wanted to actually get to all of the presentations. But, once you have enough, then it's not possible because a lot of them are going on at the same time.
Now, I understand that this research is also continuing, like one example would be your work for NIACC. Is that something you can talk about at all?
Yes. Essentially, there's a NIACC contract that's been won by a team that I've been working on, so I can talk a little bit about it. But essentially what it is it's a proposal to start building things like O'Neill colonies and bigger. But the actual approach to building them is different in that we use robotics and autonomy and standardized techniques using tensegrity and other things that are going to allow us to get very large-scale structures built in space. This would, of course, also relate to space solar-powered satellites and other things like that, plus starships, cycling ships to go to Mars, etc.
Well, now that you've mentioned O'Neill colonies, what would the best place be for that first space colony? Would that be on the moon, or would it be in a Lagrange point space station?
I would say that the first place to send it, from my point of view, and not everybody agrees with me, of course, is on the moon itself. The reason for that is that you're there in a gravity field, and it's easier to build something if there's an up or down, plus raw materials right there, plus the ability to actually easily move things around and put them into alignment, etc. So it's easier to build in a gravity field. But that doesn't mean you can't do it in space, because you just have to use different techniques. And so the big advantage on the moon is that the raw materials are there and the processing plants are local, etc.
Well, if we begin with the moon, is there any reason after that for the L-point space stations, like maybe as staging areas for exploration deeper into the solar system, or does a lunar base pretty much eliminate the need for those?
If you're going to be going to places deeper into the solar system, you want to actually start in places that are not far from the solar potential. Earth is inside of a gravity well. At the point where the gravity well of the Earth stops and merges with the gravity well of the Sun, when you're on the Sun's gravity well and not really affected by the Earth, you're on what's called the solar potential, the solar gravitational potential. So in order to go somewhere in the solar system, you have to get on the Sun's gravitational well. And the closer you are to it, the easier it is to drift away from the Earth and start your journey to somewhere else in the solar system. And so I would say that the good places to be are at the Earth Moon L1 or L2, because those things are only about 1.8 megajoules per kilogram to get to the solar potential, or at L4 and L5. Even better yet is if you're at the Earth-Sun L1 or the Earth-Sun L2. Those are places where you can actually build things. There are lots of assets that are already there, and it doesn't take very long to actually get raw materials or partially finished materials from the moon to those locations.
Oh, okay. So in that case, then the moon would actually be the staging area to move things to the L point.
Well, yes. Essentially what you want to do is you want to actually have as much of your manufacturing facility in one place as possible so that you can dig up the lunar regolith and make what they call millstock materials, what would be called millstock materials. Essentially Lowe's on the moon. I don't know if everybody's hardware stores are called Lowe's, but it's essentially a big hardware store where you get building materials. And then you would be able to have centralized manufacturing, et cetera, or chemical processing and other things like that to produce these modules and to produce the propellant or to have the rail gun or whatever it's going to take to actually get it off to the moon and on its way to the assembly point. Sort of like building an aircraft carrier. You build all the modules in the shops, and then you lift them up and you move them over to the dry dock, and you lower them down and weld them in place. So L1, L2, the various range points would be the dry docks.
Okay.
And the shops would be on the moon.
Well, you've talked about the colonies on the moon starting with underground habitats and having a dome that would be built above them, right?
Yes, and the reason for that is that while you're there, you need to actually protect yourself from the radiation. And so you need to actually build some place that has radiation protection. And after you go several meters underground, the radiation is almost nothing, and the temperature variation is almost nothing. And so it would be useful to build a stable shelter underground on the moon. That doesn't mean you have to stay in a shelter. You could be in habitats that are on the surface. But if a very large solar proton event were to occur, then you could retreat into the shelter to protect yourself until it was over. And I actually wrote a presentation about building a giant dome city on the moon, and set it up so you could actually build all your shops, all of your what would you call it, chemical processing facilities, and all your habitats underground, so that you would have a place to go if, for instance, there was an event that damaged the dome. And you could save quite a bit of the atmosphere, as I would say actually most of the atmosphere, by using condensation to condense the atmosphere in through apertures and save it. But you need to go somewhere if you have a major event that causes you to depressurize the dome. That's another reason why I came up with the idea of this city. And also, instead of having doors and things, like apertures in the dome, what you do is to get out of the dome, you simply go underneath and then take the subway to some other portal where you come out on the surface. So those are the ideas that I had when I was describing how you would actually build a city that big and how you would get in and out of it.
Now, in terms of the dome itself, you've described building a dome 25 miles in diameter that's up to 5,000 feet high in the center, but enclosed in S-glass that's only 17 inches thick. Can you describe that a bit for me?
Yes, S-glass is this type of glass that is stronger than steel. And as I described the S-glass there, I said that what would be required to build this thing is something that's as strong as S-glass that is 17 inches thick. The only issue is you can't build an S-glass dome that's 17 inches thick just from like construction methods. But you can build other things that are equally as strong, which is the final form of the dome that I came up with. But I was trying to figure out whether it was physically possible at all to even do this. And the thing that prompted me to do this is I took a look at a NASA photograph that had been passed around in many briefings, and it showed this dome city over, I guess it was Shackleton Crater. And I looked at it, and I was kind of skeptical as to whether you could do it. So I sat down one day to start proving that it couldn't be done. And in the process, I found out that it could be done, and that it could be done if you had magically appear a dome made out of S-glass that was 17 inches thick.
Okay.
Now, that didn't say how you would protect the dome, because it would be exposed to, like micrometeorites or rocks falling on it or whatever. And if it was one single glass dome, then the whole thing would be destroyed. So really what you wanted to do was build it out of facets, which is what I came up with finally. S-glass is unbelievably strong, but it cannot maintain its strength if it gets moisture on it. And so you would have to find a way to protect the S-glass from moisture on the inside and from chunks of ice hitting it from the outside, etc. And so what you come up with is something that's heavier than S-glass, meaning that, it's much thicker than 17 inches, and the actual mass of it can balance the upward pressure of the atmosphere. And it's made in facets so that you could actually remove a damaged facet and replace it. And also, if you're making it out of facets on the surface of a sphere, then you can actually have just a few actual tiles that you would make that would actually tile the entire surface of the sphere, so you aren't really manufacturing a bunch of different things. It's just maybe one or two different parts that you're manufacturing, and just replicate that, thousands or millions of times in order to actually make the dome.
Yeah, and I guess that brings us to self-organizing systems, which is something that you've described where the dome might actually be built by machines from smart materials that might have the equivalent of barcodes on them.
Well, the way that works is that, you got two choices. Either you use artificial intelligence and, smart machines in very mobile, agile robots, or you use astronauts with wrenches. And if you're going to build something that's that big, you can't even have iron workers. You need to actually have something that can put many of these things together without risking people's lives, and doing it in a very quick, efficient manner. You need to have essentially robots making more robots, sort of like in that Disney's version of The Sorcerer's Apprentice, where you keep chopping up the brooms and it keeps making more brooms. And you have those things put the systems together. And that doesn't really take a lot of trouble. It just says that you need to have like a navigation system. You need to have very good metrology. You need to have very good robots that are agile, that can climb and easily carry things that are quite heavy and line them up correctly and then either bolt or weld them together. So when you look at that, that is a self-organizing system. What you do is you just provide information, and the particles, namely the robots and the pieces, go and build this dome. And this idea of self-organizing systems goes all the way down to the lasers that you would put in your communication devices using wavelength routed all optical networks and things like that that are going to actually provide the basis for the artificial intelligence. Even those things can be built with self-organizing chemical systems.
Oh, okay. So it truly is kind of a self-organizing, self-replicating factory then. Now, you described virostructures as well, which might be kind of a nanotech variation on this idea, right?
Yeah, the viral structures referred to something that came out of Cal Poly Pomona. After they'd seen my briefing, they came up with the idea that you would have, once again, a bunch of small robots with, essentially you have pieces that have IP addresses. And so every component that's going to go in has an actual IP address. And you can send information to it and say where it's supposed to go. and the robots can talk to it and find out where it's supposed to go and what orientation it needs to have. And you just sit, in front of a monitor and you watch the whole system build itself.
Oh, okay.
And what you need to add to it is the energy. You need to add the raw materials and the actual structural form, namely where the things are supposed to go into space, what they're supposed to connect to, or what the structure is supposed to be at various stages of the construction, because you just can't construct a dome. You have to actually build a system to support the dome while it's being fabricated. And once it is fabricated, you take these other systems down. They're like scaffolding.
Yeah. Well, now, once you get the dome together, I guess the next piece there is putting an atmosphere in it. And I understand that one of the difficulties there is that the moon doesn't have enough nitrogen, right?
Yeah. When I actually wrote that briefing, the nitrogen was suspected to be somewhere around 100 parts per million. And when you consider how much atmosphere is required for a dome like that, and what the actual concentration is of the nitrogen in the rock, you find out you have a very serious problem. That building the dome is a certain level of difficulty, but that finding the atmosphere is several orders of magnitude worse than the problem building the dome.
Okay.
And so then you think some people who understand these things say, well, we're going to have to go somewhere where we can get an atmosphere, so we go off to the moons in the outer solar system when we come back with the nitrogen. And that's a supply train, but it's going to be required. But what's happened since I wrote all that was that the L-Cross actually hit the moon, and we found out to a greater degree what was in those polar craters or in the polar regions. And one of the things I was hoping for was ammonia. And so it turns out that the concentration of nitrogen is much higher than 100 parts per million. So that problem is ameliorated to a greater or lesser extent. We'd have to actually continue to characterize the amount of ammonia that's in the polar craters in order to find out how much of an amelioration there is to the problem.
Now, once the atmosphere is in place, I guess another component is power. And you had described embedding solar panels into the dome, which allows it to basically generate solar power from the dome itself, right?
Yeah, you can say that 20% of the area of the dome could be photovoltaic panels, but there are other things that can compete with that. And so you can say, okay, 10% of the dome is photovoltaic panels, and then another 10% is like transceivers for making the dome into a radio telescope. So essentially you could just take the dome area and then you could actually multiply it by a number of factors that would deal with view angles to the sun, so you could find out what your maximum and your minimum power is going to be. And the idea would be to actually use some kind of storage system consisting of either cryogenics, which would be the easiest, so that you would have a very large reservoir of cold material, or you would use some type of chemical batteries, or you would use some type of thermal wells, meaning that you would actually melt the lunar regolith underground, so you'd have a large reservoir of essentially magma underground that you could use as a heat source to augment your power when you had low view factors to the sun.
Well, with energy and with atmosphere, I guess the only remaining component there, and this would tie into the atmosphere as well, is water. Is that something that might be found on the moon?
Actually, you can find water on the moon at the equator. You can take a cubic meter of regolith at the lunar equator, and with that you can actually generate a kilogram of water simply by heating it up. What's happening is there is hydrogen absorbed onto the particles of regolith, and the surface area is so high that there's maybe 60 to 100 parts per million. And there's iron oxide there, and if you heat it up, what's going to happen is that the hydrogen is going to reduce the iron oxide, take the oxygen away, and turn itself into steam.
Okay.
That can be condensed, and so you're going to get a kilogram of water for a cubic meter of regolith at the equator. Now, when you go higher in latitudes, that increases, say, at 80 or 90 degrees, you're going to get 10 times that. So you get 10 kilograms of water. And in the polar craters itself, based on the lunar prospect data, you would get 34 times that. But now we have the L-cross data, and what it says is that the place where the L-cross actually hit the surface of the moon, they got readings of something on the order of 5.6 plus or minus 3% water. That means it could be anywhere from 5.86 to 2.6 weight percent, meaning that if you had a ton of regolith, 10% of that is going to be 100 kilograms, and 8% of that is going to be 80 kilograms of water, or essentially you would have 56 kilograms of water for every ton of lunar regolith. That's quite a bit of water. It's more water than anybody needs.
Yeah, and it sounds like if you've got water, you have atmosphere, and you have power, it sounds like that might be able to become completely self-sufficient, which I know is something that a lot of people are excited about given the cost of transporting anything out of the Earth's gravity well.
Well, the water, the atmosphere, and the actual structure provides you with something where you can drink, you can breathe, and you have a stable environment. But you still have to eat, and you're going to need to actually produce a range of plants and animals in order to have a diet that's sufficient to keep you healthy. And so there is the issue of sustainability that we have here. And on the moon, it's slightly more difficult, but it's not impossible. And the bigger the habitat that you have, the easier it is to actually get all those things correct.
Yeah, yeah. Well, another thing that you might be able to create with the water is propellant and fuel, right? You use solar power to create propellant out of the water, and you'd said that if ammonia is available, I guess that might potentially be another fuel source as well. Does that sound accurate?
Well, the reason why you want ammonia is you want to have a propellant that will actually stay in the tank without a whole lot of trouble. When you're dealing with cryogens, you have to actually continuously cool them, because otherwise they'll change into a gas. And so there's a lot of work that needs to be done in order to keep the cryogens in like a liquid state. Whereas with nitrogen, you can make a number of different types of storable propellants that will stay in a liquid form at normal atmospheric pressures without a lot of trouble with refrigeration machines. So it makes it easy if you use storable propellants than if you use cryogens. Nitrogen allows you to make the storable propellants.
Oh, I see what you mean. So you can generate oxygen and hydrogen, but then storing them becomes yet another energy drain on the colony. And so if
That's right.
yeah, that makes sense. Well, so it makes sense also that this colony would be in a lot better position than we are here on the surface of the Earth to explore the solar system, right? Because they'd be in a shallow gravity well. So would that be kind of an incentive to develop one of these colonies, I guess?
The moon is 2.8 megajoules per kilogram below the solar potential. That means if you add 2.8 megajoules per kilogram to your material, it will actually leave the Earth's environment. In order to do that from the surface of the Earth requires 64 megajoules per kilogram, which is 20 times more, essentially. So launching something from the moon to the Earth's solar potential is much easier to do than launching it from the Earth's surface. Launching it from L2 or L1, it's even closer to the solar potential. It's around 1.8 megajoules per kilogram, so it's even easier than launching it from the moon. So, if you're going to be doing outer solar system work or even put up scientific instruments to various places in the solar system, you want to do it from places that are close to the solar potential. The moon happens to be like a nice place to get resources in order to do that. So that's one of the reasons I've been working on this stuff for many, many years.
Well, now, in terms of having people up there doing work and colonizing the moon and stuff, even if they're protected inside of a dome, I've heard concerns about microparticulate dust getting into suits, getting into airlocks, and ultimately potentially causing lung and respiratory issues. Is that something that's been addressed yet?
That's something that blew up into a big problem. It was discussed for years with a bunch of hand-wringing. You can deal with it with toothpaste. essentially, what I'd say people weren't seeing was that the smaller it is, these micro shards of glass, the more trouble they cause, but the more surface area they have. And you could take diffusion-limited processes. When you increase the surface area, that increases the productivity. And the glasses are basically made out of silicon oxides. And silicon oxides are very susceptible to things that have fluorine in them. Hence, toothpaste mixed in with the sealing material and spacesuits and everything else. And when I say toothpaste, I'm just kind of joking about something that has free fluorides that can be donated in order to destroy the silicon matrix on this particle that's, say, 60 microns that looks like an arrowhead, and it's going to actually do a random walk through the membrane on your spacesuit and cause it to become perforated. Adding anything that can donate fluorine will stop that. What it'll do is it'll change these sharp pieces into things that are basically like pieces of chalk that have no sharp edges on them at all. And so there are a number of ways to deal with this space dust, and I haven't seen many at all in the literature. That doesn't mean it doesn't exist, because I haven't really been scouring the literature, but you can actually deal with all that stuff chemically with almost no trouble whatever.
Oh, okay. Now that's when they're outside, and then when they re-enter an airlock, could they just do kind of a wash in water to take that off, or would it be too difficult because of the size?
You can actually essentially do a wash with like I said, once again, something that has as much free fluorine as toothpaste, and it'll do exactly the same thing. Essentially, what you need to do is get it off of your suit, out of your bearings, and other things like that, and just dissolve it.
Yeah, that makes sense. Well, another aspect of this is potential muscle atrophy and bone density reduction from the reduced gravity. I'm wondering how much that would affect colonists, and if it means it would be kind of a one-way trip for people who were working on construction of the dome.
I remember people won't be working on the construction of the dome. There's no touch labor for almost anything there. But the issue of the physiological effects of gravity that's different from the gravity on the Earth is a problem. And essentially what needs to happen is we need to take advantage of the more advanced research that we have coming from medicine and physiology. So people have known that this is a problem for a long time. And I actually was involved in setting up a conference at the National Academy of Science called Research Enabled by the Lunar Environment. And half of the presentations there were based on ways to actually characterize and ameliorate the problems associated with the adverse effects of the space environment on the human or animal muscle systems, circulatory systems, nervous systems, etc. And people can actually go read those conference notes or get them off my website, etc. But there is a serious problem associated with the space environment, namely the gravity environment, with many of the body systems. And it's not just humans, it's just, for instance, mammals. Or I don't think that, for instance, it would make any difference whatever to marine life, because they don't feel gravity anyway.
Sure. Well, with all of those things in place, how much do you think that the total cost, approximately, would be to build this lunar colony? And how long do you think it would take to build?
I think I said it was 15 years. It has to do with, first of all, the types of machines that are needed for it, how many of them are needed, and the energy that goes in, because you cannot produce anything at any rate unless you have the energy that's required to match your production rate. So it means that if you're going to have a certain production rate, you have to have the energy systems that are going to allow you to do it. Now, one of the things we can do is on the moon, we have a significant amount of solar power available, and you can collect that power and you can store it so that you have the ability to have a surge pile of energy. So you can actually use more or less of the energy depending on what you're doing in a particular construction period, and that the surge capacity allows you to buffer the energy usage versus the energy accumulation from the sun.
Oh, okay. So that would solve kind of the construction part of it. So it'd be about 15 years. Now, is there even kind of a speculative budget on what the cost might be, or is that still up in the air?
If you do this correctly, and we looked at this, we were planning a private lunar mission about 6 years ago. There are a number of different business models that allow you to do things for the Earth that can actually bring in revenues, which means that once you get past a certain point, the activities on the moon can be self-sustaining. So you need to actually get from the initial phases to the production phase where all you're adding is information, and all the manufacturing is being done using the energy you're getting from the sun. So that the only real issue you have is where are you getting your reagents or getting your exotic electronic parts, etc., that you could do on the moon, but it may not be cost effective. And you're pulling these things with supply trains coming from the Earth. So the way we were looking at getting space solar power going was to actually go up and set viable businesses on the moon. So the very first time we send power back from the moon, namely in the form of radar beams, down to antennas on the Earth, then the thing is self-sustaining because you can actually pay this stuff off faster, very rapidly, and continue to increase your production rate of energy. And that pays for everything else that you're doing on the moon.
Oh, okay. So there would be an investment.
What we're looking at is bringing the gross world product from roughly $40 trillion a year up to around $860 trillion a year by selling power all around the Earth.
Yeah.
Bringing everybody's standard of living up to ours. So this thing is a money-making thing for everybody starting in about 13 years. From, a standing start to 13 years to the first light from the moon. Then after that, everything pays for itself.
Well, can you tell me a little bit about the project that you were trying to put together to actually realize this vision?
Well, what we had before was we had a number of different, and this was with Klaus Heiss, who used to be one of the chairmen of the Space Colonization Technical Committee. He actually came up with a business model and had been working on it since around 2002 of coming up with viable businesses that you could place on the moon, like secure data storage, for instance, like having an actual detector on the moon. If you'll remember, we're building something in Texas called the Superconducting Super Collider. And the people who benefit from that were the particle physicists. And if you actually go build a 10-meter cube of ice on the moon, what you're going to get is a detector that will be able to detect things that happen, say, 3 or 4 times a year, particle events that could have never been produced in Texas, which means that superconducting super collider didn't have enough energy to make these types of events. But on the moon, you would, because the cosmic rays can actually get to such a detector without going through the atmosphere. And so you would see particle events that you could never have even gotten with the superconducting super collider, which means that you could have actually saved a lot of money, namely the cost of the superconducting super collider, and still have gotten all that data, and it's still possible. We know all this because when Klaus Heiss decided, okay, well, we're going to actually try to come up with colonies on the moon, etc., and here are some business options, he actually formed something called a Moon-Based Coalition, which is hard to find on the net now, but it's still there. And the point was to bring in a lot of people from international locations, a lot of scientists, etc., and have them figure out, what's the advantage? What could you do on the moon that would be worth money? And there were 3 meetings, about 3 days each. One was at the National Academy of Science at the Keck building, where the National Research Council is. Another one was in Milan, Italy, and the other one was in Moscow. And all of those, all the findings of all those meetings are online in various places, and it keeps changing because people keep taking them off and putting them back on. But just talking to the people who are responsible for it, we could actually get all that information put back on the web. And it's a phenomenal amount of information on opportunities to actually use the moon for a lot of things, to solve a lot of problems. And I was involved in that. Then we took the findings from all of those meetings, and we used them to make the business plan. We actually went to institutional investors and got a commitment for $750 million. Actually, it was $700 million. My role was to go get the engineering teams that could do this and go find a way to get discounts on launch vehicles. And I won't say the actual prices, but we got phenomenal discounts on launch vehicles. And we had the best engineering team of the 20th century on this. This team was from what was called the Space Skunk Works. It was managed by Mike Griffin and Pete Warden. They did the DCX, Delta 180, 181, 183, 2 low sats, the Misty, Clementine, and DCX. And they did those things in very short periods of time and at very low cost. One of the things that made it possible for them to do it was to operate in a badgeless environment and dispense with the normal nonsense that you see in aerospace, like management, et cetera, and have everybody operating without a badge so people could talk to each other, and a lot of the social ills of operating a big company are gone. And they were able to get phenomenal results. The results were so good that the Russians complained to the United States government that having this kind of research going on was destabilizing in the Cold War. And so Clinton shut them down. But once I was transferred into Boeing from Rockwell, through McDonnell Douglas, I was pulled right into the Space Skunk Works. That's how I learned about them and found out, how well they performed, et cetera. And those are the first people I went to in order to find engineers to do this private lunar mission.
Oh, okay.
Private lunar mission was canceled because of politics, but I'm thinking about starting it up again. I might be able to pull this off. Either you have the money and no engineering people, or you have the engineers and no money. So, right now, we're in a situation where we can actually get the money, and there's no longer limitations on it. We actually, with our business plan, had gotten, 700 million in commitments with a stipulation, which I really won't go into. But the stipulation didn't work out. The stipulation should have gone to the Ballistic Missile Defense Organization, but not NASA. So that's the reason why we didn't do it.
Sure.
Right.
Well, Ed, we're almost out of time for today, but I'd like to thank you again for joining us. I can't tell you how much I appreciate your joining us discussing this. And if people want to learn more about your work, they can visit your website at explainingtheBigPicture.com. Can you tell me a little bit about the website and what's on it?
Essentially, it has quite a bit of information about space solar power and issues associated with power, period. And it has most of the briefings that I got cleared to give when I was working at Boeing. It has my resume, and it has a bunch of links.
Well, again, that's explainingthebigpicture.com. And Ed, thank you again for your time.
All right, thank you very much.
Thanks.